This is your Army in action. An Army that has established throughout its history a solid record of achievement. It's a great fighting team that has distinguished itself in battle, most notably during 2 world wars and the conflict in Korea. It's an Army ever ready, trained for decisive action, and a formidable deterrent to limited or all-out war. Your Army has also built a tradition of accomplishment in other fields. Half a century ago, it moved mountains to achieve the miracle of the Panama Canal. It organized the best scientific talent in the nation and harnessed the tremendous energy of the atom. Today, in this missile age, men of the United States Army have been pioneering in the development of rocketry, spending long hours in classrooms and in the field, testing new theories and techniques so as to be ready to meet the challenge of the future. When such a challenge came in October 1957, the challenge of Sputnik, the Army was ready to meet it. On November 8th, the Secretary of Defense ordered the Army Ballistic Missile Agency in Huntsville, Alabama, to prepare to launch a satellite in support of the International Geophysical Year program. General John B. Medeiros and his crack team of missile scientists, headed by Dr. Werner von Braun, eagerly set to work. Static firings rigorously tested performance of the main stage rocket, a modified Redstone missile, in a race against time to meet a destiny only 84 days away. Meanwhile, across the nation, in Pasadena, California, other preparations were in high gear. At the Army's Jet Propulsion Laboratory, operated by the California Institute of Technology, urgent conferences took place. Army Ordnance experts joined Dr. William H. Pickering and his staff of scientists to plan JPL's role in the American probe of outer space. Their job was to furnish the high-speed upper stages of the Jupiter Sea system and to construct the Explorer satellite itself. These men of science had long experience in Army missilery to help them solve the intricate satellite problem. Their efforts had previously helped make possible America's first supersonic surface-to-surface ballistic missile, the Army's Corporal, now stationed overseas. These scientists found the answers that enabled construction of the satellite to begin. The skills of many craftsmen were put to work. Sheet metal was bent and welded to form the outer shell of the satellite. Machinists worked wonders with metal and plastic. Components were meticulously tested to make sure they would function properly. Rockets that had to give peak performance when spinning at high velocity. Radio transmitters too, spin tested and vibration tested. These relentless trials proceeded until the assembly of the satellite was finally at hand. The last stage rocket and its satellite measured about 6.5 feet long, half a foot wide, and weighed about 31 pounds. The satellite itself tipped the scales at a little over 18 pounds. Its payload of instruments, 11 pounds. Data were sent to Earth by 2 radio transmitters, each weighing about 2 pounds with batteries. The high-power one was designed to stay alive for several weeks. The low-power one for several months. Cosmic ray intensity was measured by this assembly, which contained a Geiger-Müller tube. Micrometeorite data was obtained by means of a microphone located on the exterior of the satellite. The microphone detected high-velocity meteoric dust which infests space. At the rear of the satellite and still on its outside skin, gauges recorded the same effect. These gauges were a series of grids made of extremely fine wire that registered each time a grid was broken by micrometeoric dust. To measure temperature, on the outside were two highly sensitive gauges called thermistors. Another temperature device was located inside, behind the instrumentation, and still another here, inside the nose cone. The ingenious instrumentation for the cosmic ray experiment was designed by Dr. James Van Allen and his associates at the State University of Iowa. Meanwhile, other special equipment for telemetering and tracking was being checked out while awaiting the arrival of Jupiter-C and Explorer-1 at Cape Canaveral. Microlock and mini-track systems extending 5,000 miles downrange from the Cape to Britain's Ascension Island and at key receiver sites around the world. Antennas awaited arrival of the huge missile. The gantry crane waited. Now, in these last few days of January 1958, Jupiter-C arrives and is borne from the airfield to the fitting out hangar to undergo its final test. The bucket of solid fuel rockets undergoes a spin balance test, with Explorer-1 participating. The inertial guidance system of the main stage is also carefully checked. Then the bird is moved to the launching pad and into position. The spinning bucket is freshly painted before being placed on top of the main stage. Weather report, high velocity winds at 40,000 feet. No abatement in sight. The time for launching is postponed 1 day. But the wind velocities increase. Again, the firing time is set back. On January 31st, the upper level winds diminish to 120 knots. General Medeiros decides to wait no longer. Inside central control, the firing party goes into action. Step by step, circuits and recording instruments are checked out. Outside in the launching area, other technicians groom the huge bird for its plunge upward. Fueling with powerful hydine and liquid oxygen is completed. On the Cape, an air of cautious optimism prevails. The countdown is on schedule.
Finished fuel loading. Take a weight reading. Okay. Check the utility room fuel vapors and notify the blockhouse when we're clear to start generators. Control voltage on. Gyros on. Gyro erection on.
Regulator off. Charlie 110 recorders on. Recorder on. Everything. Okay, we'll start now.
Check that lock loading has been completed.
Regulator off.
Roger.
Charlie 110 recorders on. Recorder on. Okay, we'll start now.
Connect assembly to igniters. Okay, tie down the lead.
Regulator off.
Roger, and install your protective cap. Okay?
Regulator off.
Weight reading after last scaffold is removed. AFMTC telemeter calibration tape on. Start vibration and RPM recorders. Check all operating lights and meters for proper operation. Power panel check.
Power panel okay?
Control panel check. Roger. Measuring panel check. Roger. Cluster control panel check. Roger. Gyro erection off. Rudder drive on. Power transfer test on. Observe and record all voltages. Power transfer off.
Huh? Yeah. 021, deflection of jet main number 2. We've either got a relay kicking out or there's something dropping down on the jet main instantaneously here.
Hold. Telemeter indicates the jet vane 2 is deflected. What do you want to do? Forget it. Okay, resume count.
Okay, shall we go ahead, Jim? It looks like it. Yeah, sure.
30 seconds. Recording's on. 25 seconds. 20 seconds. On to start package. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Firing command. Fuel tank pressurized.
10:48 hours, Eastern Standard Time. January 31st, 1958. For another 2 hours, they would sweat it out. At the Cape, in Huntsville, and in Washington, waiting for the tiny satellite to race around the Earth and confirm the fact that Explorer 1 was in orbit. At last, General Medeiros could tell Washington the good news. The Army had come through. The challenge had been met. Within 2 months, other satellites would be borne aloft in a quest for knowledge that would unlock secrets in space long concealed from earthbound man and enable him to break free at last from the shackles of gravity. Beyond these first probes lay exploration of the moon, even the planets of our solar system. And beyond this, the universe itself.